All right, our last speaker for this morning's session may look familiar to those of you who were around last summer. So this is Linnea Dahmen, who's been here, actually this is her third summer at Carnegie. She's returned again to work with Decker, and she'll tell us today about her project, past AGN activity in a post-Starburst galaxy. And I failed to mention, sorry, she's a rising senior at Pomona this year. Go ahead, Linnea, whenever you're ready.
Thanks for the introduction, Gwen. I'm super excited to be back and to tell you all about some updated results from my project. So the best way to introduce my research is to ask the question, why do post-Starburst galaxies stop forming stars? So the topic of quiescence and quenching of star formation has long been discussed in astronomy, but it really hasn't been all that discussed in the realm of post-Starburst galaxies. And there are quite a few mechanisms that could potentially quench the star formation in the galaxy, and one of those is an AGN. So we explore the impacts of past AGN activity on the galaxy PGC 043234. So I should probably define a few key terms before I dive into my analysis. So a post-Starburst galaxy is a galaxy that has had a recent burst in star formation and has since stopped forming stars rather abruptly. An active galactic nucleus is gas accretion around a central supermassive black hole that releases signatures of ionization throughout the galaxy, leaving signatures in the emission line spectra. And a VORWARP is an extended region of gas that is lit up by intense radiating ionization, either by shocks or AGN. So the next natural question is to ask why we even care whether post-Starburst galaxies form stars or not, and why we care what sort of mechanisms are preventing this star formation. So one reason is that post-Starburst galaxies actually contain the material to form stars, but they aren't using it. So in 2015, Decker did a study of post-Starburst galaxies and mapped their molecular gas mass and compared them to other types of galaxies. So if you look at this figure, there are three types of galaxies. We have early types, which have stopped forming stars a long time ago. Post-Starburst galaxies, which I defined as stopped forming stars rather recently, and then star-forming galaxies, which obviously are still forming stars. And so if we look at their molecular gas masses, which is the material that stars are formed from, we see that actually post-Starburst galaxies are really similar in molecular gas mass to star-forming galaxies. So that suggests that there is some mechanism preventing these post-Starburst galaxies from utilizing the star-forming material. And for context, we have, this is where the galaxy we're analyzing falls in terms of its molecular gas mass, and we approximate this with Y's flux ratio derived from YESUF 2017. So when we first looked through images of this galaxy, we noticed the VORWARPs lit up in wavelengths associated with AGN-like ionization. But this galaxy is interesting to us for a number of reasons. So obviously it has those VORWARPs. It's also the host of tidal disruption event Assassin 14Li. It's a post-Starburst galaxy, and it has IFU data. So we're going to utilize MUSE data to constrain the history of ionization to better understand the environmental conditions for star formation. So let's talk a little bit about what MUSE is. MUSE stands for the Multi-Unit Spectroscopic Explorer. It's an integral field unit, which is really great. It takes a spectrum at every single pixel in the field of view. So this allows us to have really high resolution spatial information about where in the galaxy different spectroscopic phenomena occur, like ionization from an AGN. So our data has a wavelength range of 4,800 angstroms to 9,300 angstroms, and our galaxy is at a redshift of 0.0206. So to process our data and to extract information about the emission line fluxes and the kinematics, we use a software called PPXF. So that stands for Penalized Pixel Fitting, and it was written by Michelle Capillari, which was coined in their paper from 2004. So it extracts the stellar or gas kinematics and stellar population from galaxy spectra via full spectrum fitting. And they utilize stellar population models from Vazdekis et al. 2010. So this image is actually from when we put our data through PPXF. And in black here, you can see the galaxy spectrum. You can also see the stellar model fit and the variances. And then at the bottom here is a map of the mass fraction, which shows the corresponding PPXF solutions in different metallicities and age intervals. So again, when we looked at an image of PGC 043234, we noticed that it was lit up, the Vorwerk was lit up in emission lines that are associated with intense AGN-like ionization. And we had a hunch then that there was AGN activity occurring. So the first step is to then check whether that AGN activity is happening currently. And the best way to do that is to use a BPT diagram. So a BPT diagram takes ratios of different emission line values. So every single pixel, because of this IFU data, has its own unique spectrum. So every single pixel has its own unique values for each emission line as well. So we take the ratios of those values, where the numerator is more intense AGN-like ionization, which is our O3 and S2 transitions. And then the denominator is less intense ionization, like from star formation. And that's going to be our H beta and H alpha transitions here. And so once we apply these ratios to every single pixel, the resulting location of each pixel on this chart corresponds to one of three ionization categories. So we have up at the top, we have Seifert-like ionization, which corresponds to AGN, or more intense ionization. And then we also have star-forming ionization, which is the less intense of the three. And then we have a liner-like ionization section, which is just in the middle. So now that we've categorized all these pixels, we place them back onto a spatial map of the galaxy to determine where this type of ionization is occurring. So this map is of the nucleus, and if you look back at this plot, the space that you're looking at is noted in the red box. So we don't notice a lot of that dark red maroon color throughout the nucleus, so we determine that there isn't really intense ionization happening and that the AGN is currently quiescent. So let's contextualize things a little bit and make a timeline here. So in Decker's paper in 2015, she found that the starburst ended about 500 megayears ago. And we know that now the AGN is turned off. So in order to fill in this timeline, we can utilize the radial extent of the Vorwerk to actually look into the past. So the Vorwerk extends 20,000 light years from the center of the galaxy. And AGN radiation, which leaves signatures of ionization in the spectra, travels at the speed of light. So that means that it takes 20,000 years for the radiation from the center to reach the outskirts of the Vorwerk. So when we're looking at spectra from the pixels on the very outskirts of the Vorwerk, we're actually looking at the ionizing radiation from the AGN 20,000 years ago. So we're really able to just look back into time and see what the AGN has been up to. So that's exactly what we did. We made a radial map here of the bolometric luminosity of the AGN calculated with the H alpha flux. So as you increase in radius and therefore time, you have a higher bolometric luminosity of the AGN. So that tells us that there is, first of all, some variability happening in the activity of this black hole. And also it tells us that the AGN was previously active, at least more active than it is today. And so another thing to note is that the bolometric luminosity goes as radius squared, and also that we do a 2 sigma cut to our data, so that sort of explains the strange envelope underneath the data that's empty. So in order to further contextualize the bolometric luminosity that we've seen in this previous plot, we overlay this relationship derived in Sacconi et al. 2014, which relates bolometric luminosity of an AGN to the mass loss rate from outflows. And so when we do this, we find that there is the probability for some moderate outflows at about 30 solar masses per year at the very, very maximum. So yeah, so with the moderate AGN activity, we have some potential for outflows. And if this most extreme luminosity of the AGN were to continue into the past, it would potentially deplete the molecular gas in 100 megayears. However, this can't be the case because the molecular gas hasn't been completely depleted. So yeah, this is just to remind you all that we know that the molecular gas hasn't been completely depleted. So let us look again at the timeline to sort of fill in what we know now. So 500 megayears ago, the starburst phase ends. We know at some point the diffuse gas that eventually is lit up and becomes a vorwerp needs to be placed external to the galaxy. And we know that it has to be done before this 20,000 year mark that we're seeing now, because obviously it's there when we look at it. And we also know that outflows are possible 20,000 years ago and are probably possible well before then. And we also know that AGN variability occurs because we still see some molecular gas. So the AGN can't possibly be at its most luminous for the all the time since the AGN has been on. And then finally, we know that the AGN is currently turned off. So the next question that Decker and I asked was, how does this active galactic nucleus affect the gas kinematics? Do potential outflows and ionizing radiation change the way the gas is moving in the galaxy? And the answer is yes. So when we look at and compare the velocity of the stars and the gas, when we look at the stars, we're seeing that classic redshift, blueshift action happening with the velocity of the stars. And when we look to the gas, clearly there's something different happening. Similarly, when we look at the velocity dispersion of the stars and the gas, just to further emphasize this, the star's dispersion is pretty low here, very uniform, and the gas, again, is pretty turbulent. So this really just confirms to us more possibility for outflows. And also, it's important to note that when we compare the gas kinematics of our galaxy to other galaxies nearby, we're seeing a lot of uniform patterns. So this is just to show that the turbulence of gas that we're seeing in the galaxy is unique, and it stands out a bit to us. So then finally, the next question was, how do the kinematics of the vorwerp compare? So when we look at the velocity of the vorwerp, we see a relatively uniform blue shift. This is unique because when we look at other galaxies that have undergone mergers with extended regions like this, they usually have signatures of both redshift and blue shift. So the uniform blue shift really leads us to believe that the gas was placed here by outflows rather than mergers, but it could have been from both. And then finally, we look at the velocity dispersion of the vorwerp. And we notice that the vorwerp stems from regions of relatively low velocity dispersion in the nucleus, and then the vorwerp itself also has relatively low velocity dispersion. So ultimately, this tells us that there's low probability for shocks because the gas simply isn't moving fast enough. And so that really solidifies the idea that the vorwerp has been lit up by AGN light echoes. So before I take questions, I would like to acknowledge Decker and Gwen for all of their support, and also all the other postdocs and staff at Carnegie that have dedicated all their time to teaching us. And I've just had 3 really wonderful summers, and I'm super grateful. So thank you to everybody who has supported me.
Great, very nice job, Linnea. Do we have questions for Linnea on this work?
I can ask one.
Go ahead, Jorge.
So you mentioned that there is a high velocity dispersion in the center, right? And you claim that it's caused by outflows. What other processes can drive the turbulence in the nucleus?
That's a really good question. So yeah, one other thing that we were considering were shocks that were driving this turbulence in the nucleus. So that was essentially what we were trying to rule out, aside from outflows.
Any other questions for Linnea?
Yeah, I have a question. I'm a bit surprised by the notion that it's the outflowing gas that may be reflecting or maybe sending the oxygen 3 line, because in many other cases has always been found that it's actually the tidal remnants of still infalling gas illuminated. And if you assume that, it explains 2 things. First, I would think that is actually the case perhaps here too, because of the negative velocity, which could show inflow. I mean, it depends where the gas is, in front or behind the galaxy. And it certainly explains, if it's inflow from a tidal stream, it explains a very low velocity dispersion.
Yeah, that's really interesting. We're looking into comparing it with some other analyses like this. So we're looking into like all these sorts of explanations, and this seemed to be one that fit now, but obviously that's something really interesting to consider, and we will definitely consider that when we move forward writing a paper.
Great, thank you, wonderful talk.
Thank you.
Any other questions for Linnea? All right, very nice job.
Thank you.